Both cmath and numpy give incorrect value of asin 10. I recently needed to quickly find the arcsine of 10. I decided to use Python to calculate it for me. Based on experience, I had expected a result in the fourth quadrant, positive real pi/2 and negative imaginary. Surprise! It returned the first quadrant result. I tried numpy.arcsine as well. Same result. While it is true that the sign of the return value is 10, I don't believe this is the standard principal value for the arcsine function. I found this same result using numpy, as seen above. Is there a Python module from which I can expect to get the standard principal values, i.e. follows the principal branch cuts, for complex valued functions? Or, is the notion of standard principal value too fluid at this point to expect consistency? Pushing through the discussion on the Wikipedia page, this URL section on complex values leads to the fourth quadrant solution. This is also true for an article, this URL, published by some mathematician on complex inverse trig functions. Wolfram Alpha gives the fourth quadrant solution.
The cmath behavior is somewhat standard, in that it's not limited to just cmath and numpy. It also matches the behavior recommended in Annex G of the C standards, at least, C99 and later, as well as the definitions laid out by William Kahan in his paper Branch Cuts for Complex Elementary Functions, subtitled Much Ado About Nothing Sign Bet. But what we're really seeing here is yet another divergence between the world of pure mathematics and the world of floating-point arithmetic. The standard behavior above is specific to mathematics performed using floating-point arithmetic, and in particular using floating-point arithmetic formats where there's a negative zero value that's distinct, equal, but distinct, from positive zero. This includes the by now almost ubiquitous IEEE 754 floating-point standard. The branch cuts in cmath match the standard mathematics ones. For example, for asin, we make the cuts along the positive real axis from 1 to infinity, and along the negative real axis from -1 to negative infinity, and as usual, the values on the subinterval, -1, 1, of the real line match the usual real asin function in both standard mathematics and the cmath module. Given that, continuity away from the branch cuts forces math.asin to agree with the standard mathematical definition everywhere except possibly on the branch cuts. Mathematically, to extend asin to the branch cuts you need to choose whether to be continuous from above or continuous from below on each cut, and the usual choice for asin is to be continuous from below on 1 inf and continuous from above on inf -1, which would give you the fourth quadrant result for asin 10 that you expect. But if you're working with IEEE 754 floating point, another option emerges. On the branch cut for asin, the imaginary part of the argument is always 0. You can now use the sign of the 0 to determine which side of the branch cut you interpret the argument is lying on. So we get, for example, this is similar to the way that the real-valued atan2 function works in most languages. Usually, atan2 0.0, -1.0, is defined to be pi, while atan2 -0.0, -1.0, is defined to be pi. The sign of the 0 is used to distinguish. Mathematically, it's a bit of a cheat, but it has some nice properties in floating-point land. For example, we get that asin z.conjugate is interchangeable with asin z.conjugate for all z, including all the floating-point special cases. And behavior on quadrants is well defined, if again you determine membership of each quadrant using the signs of the zeros where relevant. As to your question about a Python module that gives the standard values, I'm not aware of one, though it Polly mentions simpy in the comments. Or you could fudge the zero signs to force values to be interpreted the right way.
If you want to see more, please consider subscribing.